In our last lecture, we had discussed about the separable transformations, and we also got two quite important relationships. Actually, what we had got regarding the separable transformation was that if we take some column vector, that is AK star, okay, which is taken as the kth column of the A star, that we were indicating as a product of AK star and AL star, okay, and there we were composing the AKL matrix as the outer product of two column vectors. All right. So AKL star was composed as the product of two column vectors AK star and AL star in the transposed form, so that we are composing the basis image. So using this expression, we were composing the basis image rather as the outer product of the two column vectors, and we had also got this very important relationship U, that is to say the image in the matrix form U matrix was obtained as the summation over KL, both K and L varying from 0 to n minus 1, and we were summing up all the basis images having indices KL, summing it up over KL equal to 0 to n minus 1, and each KL, each A star KL was multiplied by the coefficient V of KL. So if we do that, then we can compose the original image U, okay, and the transform coefficients VKL was obtained as the inner product of the original image matrix U and the matrix which we have formed by the product of AK star and AL star transpose, that is to say the basis image, okay, the KLth basis image and the matrix, if we find the inner product of these two, that will result in the coefficient VKL. So this was a very important relation that we had got, and we will now see that how exactly we go about doing it. Now, for an example, let us consider a very simple 8 by 8 image. All right, 8 rows and 8 columns. We have got a gray image, let us say. I mean, gray level image means having various intensity levels are there, and we would like to compose that image, okay, as a series summation like this. Now, how we go about doing it? We have to consider any specific kind of transformation. Right now, I am talking in absolutely general terms, in the sense I haven't yet defined any specific AKL, okay, but considering AKL in general, I mean, if we take any specific form of this AKL such that it results in a unitary transformation, then in that case the image we can get as a series summation of such unitary basis images. All right. Now, in this I have shown the examples of some basis images. All right. Now, there are 6 different type of transformations considered, okay. I think this is the Fourier transform, this is the Cosine transform, this is the Hadamard transform, Hart transform. All those different type of transformations we are going to consider later, but let me tell you the basic idea behind it. I said that we are considering 8 by 8 images. So how many basis images are we going to have? 64 basis images we are going to have, and of what size? 64 basis images of 8 by 8 sizes are going to be there with us. So just see, in this paper we have got 1, 2, 3, 4, 5, 6, 7, 8. 8 different columns are there, and 1, 2, 3, 4, 5, 6, 7, 8. 8 different rows are there in each of these images. So this complete image, okay, which is drawn within this, okay, this shows 8 by 8, that is to say 64 basis images. 8 by 8 means 64 basis image, and each basis image is something like this. This is an 8 by 8 cell, okay, which shows one basis image, and like this, in this drawing we have shown 64 such basis images, and the basis images, they are indexed like this. I take the first row of these images. This is basis image with index 0, 0. This is with 0, 1. This is with 0, 2, etc., etc. This is the basis image. This last one is the basis image with index 0, 7. Okay. This will be 1, 0, 1, 1, 1, 2 up to 1, 7, and this is the basis image indexed as 7, 0, 7, 1, 7, 2 up to, in this case, 7, 7. So totally I have 64 basis images. Okay. Now for a specific transformation, this is shown for the Fourier transformation, discrete Fourier transformation. This kind of basis images are well defined. Okay. Once you know the composition of the A matrix, that is to say the transformation matrix, if that composition is known to you, then even basis images also you can compute. These basis images will be true for all images. These are the basis images. Now, why there is a variation from one image to the other? Because the transform coefficients, rather the VKLs with which we are multiplying this AKL basis images, okay, this VKL is changing from image to image. This VKL will change. So now what I will take, I have got this VKLs also defined. How many such VKLs are there? If I am considering 8 by 8 images, I am having 64 VKLs. So likewise I will be having V00, V01, etc., etc., all the way up to V77. We will be having 64 such coefficients. We just pick up the first coefficient V00, multiply that by the first basis image A star 00. Okay. Then we take the next coefficient V01, multiply that by A01 star. Okay. Like this, we consider all the 64 basis image and multiply with the corresponding coefficient. All right. And then I simply add them up. What do I get? I get the original image. Simply. So if I now want to represent my original image, okay, in the transform domain, simply what I have to consider is the coefficients VKL. So the array of coefficients VKL, K defined from 0 to, in this case, 7, and L defined from 0 to 7, okay, all these 64 elements which I get, okay, that will indicate the transformed image, okay, for me. Okay. So likewise, basis images, okay, have been shown for different type of transformations. So the idea of these basis images is that you just pick up the basis image, multiply by the corresponding coefficient, and you keep on adding all the basis images multiplied by their coefficients, and you get the original image. So that is the basic idea, and that's why I was telling that the relationship which we got over here, it's a very important relationship. All right. So now we will see one or two very important properties of unitary transformations before we go into some specific unitary transforms. Now the first property, okay, like I can say the properties of unitary transformation. The first property is the property of energy conservation or energy preservation, I can say. Now, what is this? Let me explain. The transformation which we are defining is that the transformed vector V. I mean, I am just representing it in the vector form. It doesn't matter whether you represent it in the vector form or in the array form, two-dimensional array form, because I discussed in the last class also that even a two-dimensional array also can be composed into a vector by row ordering. That is to say, taking the first row, then taking the second row, starting with the first element of the second row, and you keep on stacking them up and you get a one-dimensional array. So basically I am writing the energy, the transformation in the vector form. If I write, then the transformed vector V is given as the product of the transformation matrix U and the original vector U. Okay, so V is given by AU. All right, that was our transformation. Now the energy is defined like this. Okay, the Euclidean norm of this vector V, okay, which is defined as summation V k square, okay, where k is equal to 1 to n, or if I write, of course I can write it as 0 to n minus 1 or 1 to n. Let us say I am writing k equal to 1 to n Vk square. That will give me the energy of what? The energy of the transformed vector. What is the energy of the original vector? Simply given by this, which will be, let's say in this case I am just choosing my index to be n equal to 1 to n un, okay, un square, okay, will give me the energy in the original vector, and I am required to prove that the energy in the transformed vector and the energy in the original vector, they are equal. It is very easy to show that. All right, showing this equal to, of course by definition itself I am having this as k equal to 1 to n mod of, I write it in this form, Vk square, okay, which can be expressed, okay, as a product of two vectors. That is to say, I can represent this as V star transpose, that is to say converting V into a row vector and conjugating each element, okay, multiplied by the column vector, the original column vector, column vector V, okay. If I multiply, then I get a scalar. So this total V star transpose V, okay, would give me the, this particular expression, and because I have this transformation relation already defined, okay, I can write V star transpose as U star transpose A star transpose. All right, and what is V? V is nothing but A U. All right, what is A star T A? It results in an identity matrix, okay, because A star T is equal to A inverse by the basic definition of unitary matrices, okay. So this simply reduces to U star transpose U, which gives me simply this relation, which simply gives me n equal to 1 to n mod of un square, okay, which gives me the energy in the original vector, okay. So unitary transformation basically preserves energy. In a very similar way, you can show, okay, instead of taking V and U to be vectors, you take V of KL and U of Mn, and you can in a very similar way show that the energy in V, okay, is going to be same as the energy in U. Okay. So, energy preservation is a very important property. And the second property of unitary transformation is what is known as energy compaction. Now, although it is seen that the total energy in the original image and the total energy in the transformed image, they remain the same, okay, it is very often found, okay, in most of the images it is very often found that the energy in the transformed domain is generally contained, okay, or is generally dominated by only a few coefficients in the transformed image. Only a few coefficients in the transformed image, okay, they contribute to the maximum energy, okay, and the rest of the coefficients, they contribute very little to the energy. And that is why we can use it for the purpose of data compression. We can only use, okay, the coefficients which contribute to more energy, okay, and the coefficients which are insignificant, we can eliminate them out, okay, and as a result, by keeping only a few transformed coefficients, okay, we will be able to represent a complete image, because a complete image is nothing but the coefficients of the transformed image multiplied by the basis images. So, if I have only a few coefficients kept, okay, then using only a few coefficients I can construct a large image, okay. So, this energy compaction is the second very important property, okay, which the unitary transforms follow, okay. There are some more properties of unitary transformations, but right now I will not go into that. Rather, we will come across some further properties of unitary transforms as we go into some specific transformations. All right. Now, before we go into any specific transformation technique, okay, I would like to ask you that, do you have any questions? Okay. So, I can continue, or rather I can start the discussions on some specific transformation, and the transformation which I have chosen for today's discussion, okay, is a very important, very important transformation, okay, in the image processing, not only in image processing, rather in signal processing in general, and that is called as the discrete Fourier transformations, or I can write discrete Fourier transforms, and taking the three alphabets D, F and T, it is widely used in the short form as DFT. So, henceforth we will also say DFT rather than calling the big word discrete Fourier transform. Now, again I define the transformation relationship, which was V equals AU, okay, and U equals A star T V. Now, of course, this equation implied that Vk is equal to n equal to 0 to n minus 1 Akn, okay, this multiplied by Un, all right, and this was Un was equal to k equal to 0 to n minus 1 Vk A star Kn. Now, everything about the transformation depends upon our choice of this Akn, and we have chosen this akn to be like this. The element of the, what is akn? Akn is nothing but the element of the transformation matrix, okay, and akn we have chosen to be exponential to the power minus j 2 pi kn divided by capital N. So what I have basically chosen, the element of this transformation matrix in this case is chosen as a complex exponential expression. All right, this is a complex exponential expression, okay. The indices are k and n, and we find that in the complex exponential expression this k and this n appears, okay, and what I am having is simply this k n product multiplied by 2 pi by n, where capital N, okay, which is appearing in the denominator of this, okay, is nothing but the number of samples which I have, or rather the length of the sequence, because I have considered the original sequence un to be of length capital N. Right now I am defining the discrete Fourier transformation only in one dimensional form, okay. Two dimensional form is a very simple extension. Now only thing is that writing this exponential to the power minus j 2 pi k n by n, okay, every time this exponential expression writing is little bit problematic. So what I simply do is that I define a symbol, okay, that symbol is w, okay, and I keep this as the base capital N, okay. So w to the base n I define as by this expression, exponential to the power minus j 2 pi by capital N. I am just representing this minus exponential to the power minus j 2 pi by capital N by wn, okay. This is going to, this wn is going to be the same for w to the base capital N is going to be the same for the entire transformation matrix, because the transformation matrix elements are only changing in k and small n, okay. So I have taken the k and small n terms out, and the rest of the terms I have defined by a new symbol w to the base n. So in terms of this new symbol I can write a of kn as w to the base n, but what else I have to put? This w to the base n should be raised to the power k and small n. So if I choose my elements like this, okay, elements of the transformation matrix in this form, okay, the transformation that results is called a discrete Fourier transform expression. Why discrete? Because we are not taking continuous signals. If we had taken u to be a continuous signal, then even the v, that is the transform, after transformation also we would have got a continuous signal. But what we are doing in this case is we are taking discrete signal, okay, for this u, okay. The transformation also results in a discrete sequence vk. So un is the original sequence, vk is the transformed discrete sequence. So because everything is in the discrete domain, okay, by operating on the specific samples, we call this type of the Fourier transform as the discrete Fourier transformation. All right. Now tell me, what is going to be a star of kn? Correct. I have defined a kn to be exponential to the power minus j 2 pi kn by n. So if I take a star of kn, all that I have to do is exponential to the power plus j 2 pi kn by n, which results in w to the base n to the power minus kn. Okay. So by writing in these terms, okay, I can, so this is equal to w to the base n minus kn, and now I can write the transformation pair. I mean, henceforth I will call them as transformation pair, okay, Vk as summation n equal to 0 to capital N minus 1 un wn kn k equal to 0, 1, etc., etc., capital N minus 1. This is called as the forward transformation. That is, given a sequence un, we are getting the output sequence Vk. Now I should be able to do the reverse transformation also. What should be the reverse transformation expression? I think you can tell me what is going to be the expression for un, please. Sigma n equal to 0, I mean, in this case let me say k equal to 0 to n minus 1, because I have this thing defined as Vk wn, but raised to the power minus kn in this case. This was plus kn in the forward transformation. In the reverse transformation, minus kn, and in this case my index n should be defined 0, 1, etc., etc., up to capital N minus 1. Now we had said in our last class that all the properties and everything whichever we were studying, okay, those were valid for unitary transformations. Now this new transformation which is just now defined, okay, the transformation is simply defined by this expression. Does it result in a unitary matrix? Sure. Well, if you now see that whether the energy preservation property, which I just now said, the energy preservation property, whether that holds good or not, you will find that the energy preservation property does not hold good here. All right. And in order that the energy preservation property holds good, okay, we have to do not much but a bit of normalization. So if we take the forward transformation expression like this, Vk equal to simple summation of n equal to 0 to n minus 1, like this, in that case, if we want to recover un from Vk's, okay, this transformation, entire transformation must be normalized by this term 1 upon n. All right. Now, what is the transformation matrix's composition? Okay, simply the composition of the transformation matrix. If I call the matrix by F, okay, then the matrix is nothing but the set of all elements w to the base n raised to the power of kn, okay, where k and n vary from 0 to n minus 1. This entire set, if I consider, okay, it results in the transformation matrix F. But if you are considering a transformation matrix of this nature, it does not result in a unitary matrix. And in order to make it a unitary matrix, what we need to do is just these coefficients I have to multiply by a factor 1 upon square root of capital N. I repeat, I have to multiply the elements w to the base capital N raised to the power kn. These elements, every element I have to multiply by a factor 1 upon square root of capital N. If I do that, then the matrix that results is a unitary matrix. All right. So, with respect to the unitary matrix elements, I should redefine these transformations. I should not write it as Vk equal to this and Un equal to this. Rather, I should make Vk equals 1 upon, can anybody tell me what I should write in terms of unitary transformations? 1 upon square root of n summation n equal to 0 to capital N minus 1 un w to the base n raised to the power kn, okay, and of course k equals to 0, 1, etc., n minus 1. Let me call this as equation number 1, and un as 1 upon again square root of n, so that the normalization factor remains the same for forward as well as the reverse transformation. But in this case, summation index is k equal to 0 to capital N minus 1 Vk w to the base n raised to the power kn n equal to 0, 1, etc., up to n minus 1. This is equation number 2. I made a mistake. This should be w to the base n raised to the power minus kn. All right. So, this transformation pair which I have defined now is called as the unitary DFT transformations. All right, DFT itself is a transformation, so I should have called this as unitary DFT, but many a times we are accustomed to say things like AC current, DC current, and this is also one of that type. All right. So, now this being the one dimensional DFT, I can easily define a two dimensional DFT. It is just a simple extension. And what is going to be the two dimensional DFT expression? Rather, I should not write V as a function of K only, I should write V as a function of two variables K and L, okay, and that is equal to, I will write the normalization coefficient a little later, m equal to 0 to capital N minus 1 and n equal to 0 to capital N minus 1 u of mn, which is the elements of the image matrix, w to the base n km plus ln, okay, where both k and l vary between 0 and n minus 1. They are defined as integers, but integers in the range of 0 to n minus 1, okay, and u of mn, okay, is equal to summation m equal to 0 to, not m, rather k equal to 0 to n minus 1, l equal to 0 to n minus 1, and I have to do the summation over v k l, yes, w to the base n, and then minus km minus ln, okay, and definition of the indices 0 less than or equal to mn less than or equal to capital N minus 1. So, this is the unitary 2D DFT. No, it is not unitary 2D DFT. I have forgotten to do something. I have to normalize that, and I was normalizing by a factor 1 by square root of n in the case of one dimensional, and here I will simply do 1 by n in the forward as well as 1 by n in the reverse. If I do that, it results in unitary transformation, and also it preserves the energy, obviously, as a property of unitary transformation itself. All right. So, now let us see some more aspects of this transformation. Look at the transformation element over here. It is w to the base capital N but raised to the power Km plus Ln. All right. Now, just try to recollect our ideas on separable transformation. What did we say in course of our discussion on separable transformation? That the transformation element, okay, the transformation matrix elements which we get, if we can represent them as the product, okay, of two terms, one in the k direction and the other in the L direction. So, two product terms involving k and L, if we can do that, it results in a separable transformation. And in this case, are we able to do that? We can simply do that. All right. So, the transformation, the DFT transformation is obviously a separable transformation. Okay. And let us now see that how nicely we can implement the separable transformation. Now, in this case, I mean, if you want to implement a DFT algorithm, what simply you have to do is, in order to compute a single element in the transformation matrix, in the transformed domain, VKL is the element in the transformed domain of image, UMN is the original image. So, in order to get a single element of the transformed image, we have to consider the entire n by n image, okay, and we have to multiply the elements individually with the transformation coefficients Wn, okay, and then ultimately we will get this V of KL. So, for a single element we have to do n square number of computations, really speaking. But by applying the separable transformation property, okay, we will see that it can be done, okay, in a much quicker form. What I will simply do is that I will rewrite this mathematical expressions. Let me call this as equation number 3, the forward transformation for 2D, and the reverse transformation, okay, as equation number 4. Now, all that I will do is I will simply rewrite these two equations. Okay. Let us write only for VKLs, that is the forward transformation, and if I show you how to do that, then doing it for the reverse transformation is also a similar job. Okay. Now, I am writing V of KL, okay, as obviously 1 upon n term remains as before, and I had a double summation over here, summation over m equal to 0 to n minus 1 and summation n equal to 0 to capital N minus 1. Now, what I am simply doing is this Wn to the power Km plus Ln which I got, I am just separating out into two terms. I had got W to the base n Km plus Ln, and this I will write as Wn to the power Km multiplied by Wn to the power Ln. So, what I will simply do, I will take this Wn to the power Km term out and club it with summation m equal to 0 to n minus 1, and the rest of the terms I will simply keep as it is. So, that means to say, I will write summation m equal to 0 to n minus 1, and I will simply write W to the base n Km, okay, and then summation n equal to 0 to capital N minus 1 U of Mn, okay, W to the base n Ln. I haven't written anything new, okay, I have only rewritten this equation 3, only Wn to the power Km I have shifted to this side, and the rest of the term, that is Wn to the power of Ln, remains over here. Now, I would like to analyze, okay, this portion of the expression. Means whatever I am marking with the red pen over here, let me examine this term. Can you tell me what this term is? What is the significance of this term? Excellent. We have defined already the single dimensional discrete Fourier transform, okay, and if we take this expression, okay, all that results is the one dimensional DFT. And in which direction am I taking the DFT? In the n direction. And since the matrix is defined as U of mn, m is the index of the row, n is the index of column. So what we are taking? We are taking from the image, we are taking a particular row, okay, and over all the columns, okay, column number 0 to column number n minus 1, okay, for that particular row, I am taking a one dimensional DFT, okay. So let me call, okay, this one dimensional DFT as, now anytime I take DFT, the transformed image I am representing by V, okay. So V something something, what is that I will write, is equal to summation n equal to 0 to capital N minus 1 U of m n W to the base n capital L n, okay. So this results in a transformed image, all right, or a transformed column. What should I write as the index for this transformed column? Pardon? V of, there are two variables, m comma n, no, m comma m remains as it is because I haven't touched the rows as such. The rows have been kept as rows. M comma L. M comma L. Because I was originally having the image as U of m comma n.
M will cause.
Okay. And after one dimensional transformation, this n will get transformed to L. Okay. So what I have got is V of m comma L. Okay. And this is defined by this expression. Alright. Not exactly, because what I have got, okay, is that this is the one dimensional transformation should have been 1 upon n of this, and I am simply multiplying this by n. So assuming that I have taken care of the normalization factor properly, now I examine this, or rather I should be able to write V of KL equal to 1 by n summation m equal to 0 to n minus 1 W to the base n km, and what should I write over here? I will simply write V of ml. And now what am I trying to do? What is this expression indicating? Now already V of ml is a transformed image. What type of transformation? I have taken individual rows and operated over the columns, okay, to get a transformed image. And now what I will do, on that transformed image, okay, I will take individual columns, okay, and operate over all the rows. Alright? And by doing it that way, the image that results, okay, is a transformed image, and definitely the coefficient of that transformed image will now be not V of ml, rather V of KL, because m will now get transformed into the K domain, so it is V of KL equal to this. So pictorially, if I indicate that, what I have the original image defined in m and n, okay, and it was, if this is the 0 0, that is the origin, we were going up to n minus 1 pixels in m direction and n minus 1 pixels in the n direction, okay, and this we did a transformation, and after the transformation, okay, this is transformation over, I should write, this is transformation over columns and for each row, okay. So that now what I have got, this axis now becomes, rather I drew it in a, I mean I should have called this to be M and this to be N, okay. Now it results in, this direction is still M, but this direction now becomes transformed to, N becomes L, okay. So transformation of ML, this also becomes N minus 1, N minus 1. So this is the transformation column wise, and after that we will do a transformation on rows, transformation over rows, okay. And if we do that, then the image is defined like this. This axis becomes L axis, this axis is the K axis, and the image is defined with this 0 0 as origin over N minus 1 pixels over here, N minus 1 pixels over here. So simply, first this is the row wise transformation, first this is the column wise transformation, and then the row wise transformation. So now I need not, so while doing a DFT operation, I am not doing the DFT over the full n square space. At a time I am doing DFT only over an n dimensional space rather than doing it on n square dimensional space, alright. And there is yet another aspect, okay, which has to be considered. The DFT expression, okay, which we had written, okay, this was the one dimensional DFT expression, and this was our two dimensional DFT expression. Now the DFTs can be very efficiently implemented in computer by fast algorithms, and the fast algorithms for computing the discrete Fourier transforms, they are called as the fast Fourier transformations, fast Fourier transforms, okay, or FFT. The main idea behind this FFT algorithm is that we are just making the transformations more and more separable, okay, or rather the original sequence of n elements which we have, if we now partition the original sequence into subsequence, and then each of the subsequence we further partition, and then we take the discrete Fourier transforms on each of those elementary subsequences and then combine, okay, all the resultant DFT operations, okay, then it is found that instead of doing n by n multiplications, n square complexity multiplications, okay, you have to do only n log n order of multiplications. N, so the multiplication order comes down from n square to n log n, okay, and that tremendously saves the computations, okay. So any one dimensional sequence, okay, or two dimensional sequences, okay, their DFT can be implemented very efficiently using the FFT algorithms. Now FFT, I mean those who are students of signal processing or have some background on signal processing must have come across these terms of FFT. In case you do not have background on signal processing, okay, I recommend that you should read, okay, about some materials in the signal processing books, okay, either by Rabiner and Gold's Digital Signal Processing, okay, or there is also a book by Oppenheim and Schaeffer, okay. Their book is also, I think Rabiner and Gold is Introduction to Digital Signal Processing, and Oppenheim Schaeffer says Digital Signal Processing. And there is also a recent book by Oppenheim and Schaeffer, which is, I think, Discrete Time Signal Processing, okay. So you can refer to these books, and there the fast Fourier transforms algorithms have been well explained, okay. So my idea of telling this was that what we can now do is we can simply apply the fast Fourier transform algorithms for each of the rows independently, okay. Over all the column elements we implement the fast Fourier transforms, and then once again we apply the fast Fourier transform algorithm now over the columns, now over the rows and define for each column, okay. We get the two-dimensional array. And mind you, each row, in the case of this transformation, each row can be independently processed, and on this each column can be independently processed. So there is a scope to implement this algorithm in parallel. Means if you have n number of processors, then n number of rows in this case can be implemented parallelly, and the same n number of processors can be used to implement the DFT of n number of columns, okay, in a parallel fashion. So that's how one can compute the two-dimensional discrete Fourier transformations, okay, quite fast. All right. Now this 2D discrete Fourier transforms, okay, they have got several properties, all right, and we will be discussing about the properties of discrete Fourier transformations, okay, in the next class. Anybody having any questions?
After taking the discrete Fourier transform,
yes,
we are going to have phase also.
After taking the discrete Fourier transforms, we are going to have phase. All right, this is a very important question which has been brought about, okay. Now, one thing which I should have mentioned in my lecture was, what is this Wn after all? Wn is a complex element, all right. This U of Mn, in general U of Mn also could have been complex elements, okay. Of course, whenever we are talking of digital images, okay, rather when U of Mn is indicating the intensity values of different pixels in a digital image, then U of Mn is real, okay. But even if U of Mn, okay, is having real values, okay, the intensity values are real values, if we take that, then even then, because this Wn is a complex, what you get as V of Kl is in the complex domain. So it is having both the real component as well as imaginary component. So as a result of that, you are having magnitude as well as the phase information available, all right. If you want to take the magnitude, simply what you have to take is, take every complex element of VKL, okay, take the real part square, take the imaginary part square, okay, add them up and take the square root, okay, you will get the magnitude part of the Fourier transform, okay. Whereas if you are taking the real part and the imaginary part and you are taking the tan inverse of their ratios, okay, that will result in the phase information, and you can get a phase spectrum also. You can get a magnitude spectrum, you can get a phase spectrum, okay. So this is very important to note that both magnitude as well as the phase information is there in the